Imagine drifting through interstellar space while the usual cues of direction gradually dissolve. The stars remain fixed, the darkness remains quiet, yet the geometry beneath everything begins to shift, as if space-time itself is adjusting its orientation. At first, the change is subtle, a soft distortion in the trajectories of distant photons. Their paths curve away from a single point ahead, bending outward in graceful arcs. Even particles without mass, normally guided dutifully by gravity's inward pull, arc in the opposite direction. You continue drifting, but the motion of the universe around you follows a different instruction, one that points toward escape instead of capture. This is the edge of a white hole, a space-time region predicted by general relativity where the familiar sense of gravitational direction reverses. To approach such an object is to enter a domain governed by negative time geodesics, world lines that extend outward, away from a central singularity. In the language of relativity, these geodesics describe the natural trajectories of objects when no force acts upon them. Around a white hole, those trajectories flow outward like radiating filaments, mapping the geometry of a universe that evolves away from a central event rather than toward it. The horizon of this object behaves as a perfect boundary. Light that attempts to cross it inward, even at infinitesimal glancing angles, turns outward instead. The horizon allows no approach, no crossing, no entry. The outward flow is absolute. In the imagery used by relativists, the light cones tilt in such a way that all possible futures lie outside the interior. Every future-directed motion, every timeline, every causal path points away from the horizon. The surface is an anti-trapped surface, the inverse of the trapped surface that defines a black hole. If a black hole concentrates futures into a single central endpoint, a white hole distributes them across the cosmos. To sense the difference, imagine a black hole first, an object whose horizon marks the region where even outward-directed light converges inward, funneling toward a singularity. This behavior defines a trapped surface, a surface on which all future motion inevitably turns inward. In contrast, an anti-trapped surface directs every future path outward, creating a region from which matter and radiation diverge with geometric necessity. The two surfaces are mirror images in the mathematics of spacetime. The experience, if such a thing were observable, would feel like entering a domain where time takes on a different orientation. In the presence of a black hole, time points inward. In the presence of a white hole, time flows outward. The distinction arises from the equations themselves. The Schwarzschild solution, one of the earliest exact solutions to Einstein's field equations, contains both possibilities. When that solution is analytically extended, it unfolds into a space-time with four regions: two exterior universes, a black hole interior, and a white hole interior. Each region obeys the field equations with structural precision. The white hole appears naturally, emerging from the requirement that the solution be complete and continuous across all coordinate ranges. The equations do not limit themselves to the behaviors we have observed. They provide all geometries consistent with curvature, mass, and the structure of space-time. Among those geometries lies a region where the causal structure reverses direction, a region that expels rather than absorbs. To understand the scene more concretely, imagine tracking a single photon as it moves near the horizon. In familiar gravitational fields, light curves inward as if space were a gently sloping funnel. Near a black hole, the slope steepens dramatically. Photons approach the horizon along spiraling paths, losing the ability to escape once they cross it. Now reverse the curvature. Near a white hole, the funnel opens outward. Photons turn away without hesitation. Even trajectories that begin with inward motion curve outward as the geometry directs them toward increasing radial distance. The photon does not resist the horizon redefines the photon's future. This outward tilt of all future-directed paths is what gives a white hole its remarkable structure. Space-time is not repelling matter, It is shaping the map of allowable motion. No physical force pushes objects away. Instead, the geometry offers no path that leads inward. The interior of a white hole exists entirely in the past of every event outside the horizon. In a practical sense, this means the interior cannot be entered. Even if one could imagine reaching the horizon with engines capable of accelerating at thousands of g-forces, the effort would fail. Every attempt to move inward would simply extend one's future along an outward-directed geodesic. Entry is not forbidden by a barrier. It is impossible because space-time assigns no valid future to that direction. This reveals something profound about general relativity. It permits objects defined entirely by the arrangement of causal arrows. A black hole exists because all arrows point inward. A white hole exists because all arrows point outward. The mathematics accommodates both with equal consistency. These inverted causal arrows define a world where escape is mandatory. Nothing lingers near the horizon. Everything drifts outward with geometric certainty. Matter emerging from the white hole interior does so along radial trajectories that resemble a cosmic expansion on a miniature scale. In fact, the flow of matter out of a white hole shares conceptual similarities with the behavior of the early universe, an expansion sourced from a singular origin, moving outward along timelike and null geodesics. In the mathematical sense, the similarity is exact. The Big Bang itself behaves as an anti-trapped surface. This does not make the universe a white hole, but it illustrates how the underlying geometry can produce outward-directed causal flows under certain conditions. If one continues drifting through the imagined scene, more details of the geometry become apparent. The gravitational potential grows weaker toward the horizon rather than stronger, an inversion of the usual behavior. Test particles do not accelerate inward. They decelerate in the inward direction and accelerate outward. Angular momentum behaves in interesting ways as well. Circular orbits that would normally shrink toward a black hole instead expand away from a white hole, finding no stable inward configuration. Even tidal forces, the stretching and squeezing effects created by space-time curvature, reverse their orientation. Instead of pulling objects into elongated shapes along radial lines, they tend to stretch outward. The landscape becomes increasingly alien the more one studies it. Yet every feature arises straightforwardly from Einstein's equations. The existence of white holes in mathematics invites a reflection on the nature of physical law. Physics often predicts structures long before they are observed. Black holes themselves lived as purely theoretical constructs for more than half a century after Carl Schwarzschild discovered their solution in 1916. Wormholes, cosmic strings, inflationary fields, even the existence of gravitational waves followed similar arcs, first allowed by theory, then examined abstractly, and eventually, in some cases, verified by observation. White holes occupy a position on that frontier. The equations support them without qualification. They appear unambiguously in the maximally extended Schwarzschild geometry. They form naturally in certain solutions of Kruskal-Sekera's coordinates. They arise in Penrose diagrams as the time-reversed counterparts of black holes. They have never been ruled out by general relativity, yet the universe has not revealed one. This contrast, mathematical permissibility versus observational silence, forms one of the most intriguing tensions in modern theoretical physics. When the equations allow a phenomenon with perfect internal consistency, but the cosmos offers no evidence of it, physicists must decide whether the absence reflects fundamental impossibility or simply the limits of current observation. White holes lie precisely on that boundary. Their existence would imply a history imprinted on space-time that flows outward into the present. Their horizons represent boundaries beyond which the universe possesses no future-directed paths. Their geometry includes a singular past event that defines their internal evolution. Their behavior satisfies local conservation laws and global causal structures with remarkable precision. In many ways, a white hole is a portrait of what spacetime can become when the arrow of time orients itself in the opposite direction. As the scene settles, the outward flows calm into a conceptual landscape rather than an imagined one. The anti-trapped surface sits at the centre, a region where geodesics converge only in the past and diverge in the future. No object in the surrounding space carries the signature of inward collapse. Everything carries the imprint of outward expansion. It is a reminder that general relativity is less a set of rules than a space of possibilities, a mathematical atlas where familiar and unfamiliar landscapes coexist. And now that the pace has reached a gentle equilibrium, this is the right moment to breathe and offer a small invitation. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow and it keeps these journeys alive. White holes invite us to widen our imaginations not through fantasy but through rigorous physics. They show that nature may include structures we have yet to witness, but that the equations already understand, and through this doorway, an opening defined entirely by the geometry of time, the investigation continues into the mathematics that predicted these objects, the scientists who uncovered them, and the profound implications they carry for our understanding of the universe. In the earliest years of general relativity, the mathematics of space-time was still unfamiliar terrain. Einstein's theory had transformed gravity from a force into a curvature, but the rules governing that curvature were expressed through equations whose full implications would take decades to understand. One of the first exact solutions to these equations, discovered in 1916 by Carl Schwarzschild, became a foundation of modern gravitational physics. Schwarzschild found a simple, elegant geometry describing the spacetime around a spherical mass. He derived it from the field equations while serving on the Russian front in World War I, writing from the trenches to inform Einstein of the exactness of the result. The Schwarzschild metric appears deceptively straightforward. It expresses the way time slows and space curves around a mass. It describes the gravitational field of planets, stars, and any spherical body that does not rotate or charge itself electrically. Yet within this seemingly ordinary metric lies a deeper structure that only later generations of physicists recognized. The solution contains hints of surfaces, boundaries, and regions hidden beneath the coordinates. The familiar exterior, where planets orbit and photons bend, is only one part of a larger spacetime. When extended through a more complete mathematical treatment, the solution reveals not only black holes, but their geometric counterparts, white holes. The original Schwarzschild form includes a coordinate singularity at the Schwarzschild radius, a distance proportional to the mass, roughly 3 kilometers, about 1.86 miles, for a sun-sized object. At this radius, the metric components appear to diverge, suggesting a physical problem. Early interpretations assumed the solution simply broke down there. Einstein himself believed the singularity meant the model lacked physical meaning in that region. The horizon looked like a defect, an unphysical artifact. Later studies showed that the infinity in the metric was an illusion caused by the choice of coordinates. The Schwarzschild radius marks a horizon, not a physical barrier. The divergence arises from the coordinate system, much like the way Earth's longitude lines converge at the poles, even though no physical singularity exists there. A coordinate system can mislead, and in the Schwarzschild coordinates, it created the appearance of a singularity where none existed. Physicists eventually distinguished between two categories of singularities. A coordinate singularity appears when the mathematical description breaks down, but the underlying geometry remains regular. A physical singularity refers to an actual divergence in curvature, a place where the equations describe infinite density or unbounded gravitational effects. The Schwarzschild horizon is the former. The central point at r equals 0, however, is the latter, a true curvature singularity that signals extreme conditions. Recognizing the difference between these two types of singularities opened a path toward a more complete understanding of the Schwarzschild solution. If the horizon was merely a coordinate artifact, perhaps an alternative coordinate system could reveal the true form of the geometry. This idea slowly took shape across the 1940s and 1950s, ultimately leading to one of the most important reinterpretations in the study of gravity. The key advancement was the Kruskal-Szekeres extension, introduced independently by Martin Kruskal and George Szekeres around 1959 to 1960. They constructed a coordinate system that covers the entire Schwarzschild spacetime smoothly, eliminating the coordinate singularity at the horizon. Their extension produced a spacetime diagram that exposes the full structure hidden within the original metric. Instead of collapsing at the horizon, the extended coordinates flow through it without divergence. The extended geometry reveals 4 distinct regions sewn together in a continuous manifold. The first is the exterior region familiar from astrophysics, the domain where stars orbit and observers move freely. The second is the interior of a black hole, where radial coordinates act as time-like variables and future-directed paths run toward the singularity. The third region is a second exterior universe mirrored across the geometry, and the fourth is the region associated with a white hole. In this space-time map, the white hole occupies a symmetric position relative to the black hole interior. The black hole contains a future singularity. All future-directed paths terminate at a single point inside. The white hole contains a past singularity. All future-directed paths originate from it. In the Kruskal-Szekeres diagram, the white hole sits below the central cross structure, while the black hole sits above. Both are connected to the 2 exterior regions in a way that preserves the continuity of the geodesics. This geometry arises because the Schwarzschild solution is time-symmetric. If one reverses the direction of time, the equations still hold. A black hole is a region into which matter flows. Its time reverse is a region from which matter emerges. In an analytically complete spacetime, both regions appear naturally. In the Kruskal picture, the white hole interior is not a speculative embellishment. It is embedded in the same solution that describes ordinary stars and their gravitational fields. It appears directly from solving Einstein's equations fully, without artificial constraints. Nothing in the mathematics eliminates this region. Its presence reflects the principle of mathematical completeness. If the equations define a region consistently, then the full solution includes it. This completeness carries scientific weight. It ensures the equations produce a spacetime that satisfies all curvature and continuity conditions. Removing the white hole region would make the solution incomplete, breaking the smooth structure across the manifold. The geometry is crafted by the equations, and the equations allow a region that behaves like a time-reversed black hole. One of the most influential figures in interpreting these results was David Finkelstein. In 1958, Finkelstein published a short but transformative paper describing the Schwarzschild horizon as a one-way membrane. He introduced a set of coordinates, now called Eddington-Finkelstein coordinates, that penetrate the horizon smoothly while preserving causal structure. These coordinates revealed that the horizon is a surface of no return for black holes and a surface of unavoidable emergence for white holes. Finkelstein described the distinction through the behavior of light cones. Inside a black hole, the cones tilt so strongly inward that even outward travelling light follows paths toward the singularity. Inside a white hole, the cones tilt outward, forcing all trajectories away from the interior. This interpretation made the geometry physically intuitive. Instead of a mathematical curiosity, the horizon became a causal boundary, a surface dictated by the curvature of space-time, shaping the possible futures of nearby objects. Finkelstein's work demonstrated that the horizon divides space-time into regions of distinct causal behavior. It clarified why two different interiors exist in the full Schwarzschild geometry, one corresponding to collapse, the other to emergence. These two interiors represent the same solution viewed through two different orientations of time. The white hole interior emerges structurally from the time-reversed behavior of the black hole interior. In the black hole, all geodesics converge toward a future singularity. In the white hole, all geodesics diverge from a past singularity. The metric treats these two forms symmetrically. In the diagrammatic representation, the white hole occupies the lower portion of the extended spacetime, its past singularity feeding into the manifold, just as the black hole's future singularity absorbs it. Physicists soon adopted Penrose diagrams as a tool to study such structures. Roger Penrose introduced these conformal diagrams in the early 1960s to represent entire spacetimes on finite surfaces. By compressing infinite distances into manageable shapes while preserving causal relationships, Penrose diagrams reveal the global structure of solutions with remarkable clarity. In the Penrose diagram of the extended Schwarzschild spacetime, the white hole appears as a triangular region at the bottom of the diagram. Its past is bounded by a singularity, drawn as a jagged line indicating the divergence of curvature. Its future opens into the two exterior regions. Every future-directed path from the white hole interior emerges into the surrounding space. No path ever enters from outside. The diagram illustrates the anti-trapped nature of the interior with geometric precision. Light rays aimed inward bend outward, mapping the orientation of the cones. The diagram also shows the tight coupling between mathematical form and physical interpretation. Penrose diagrams make explicit which regions can communicate, which cannot, and which lie beyond causal reach. The placement of the white hole interior is determined entirely by these rules. It exists wherever the structure of the metric demands a region that plays the time-reversed role of the black hole interior. These insights illustrate why white holes arise from mathematical completeness rather than from physical expectation. No known astrophysical process generates the initial conditions required for a white hole. Stellar collapse creates black holes. Nothing observed in the universe creates anti-collapse. The white hole region exists because the equations contain it, not because nature appears to. When physicists fully solved the Schwarzschild geometry, the white hole was uncovered as a necessary component of the extended solution. Such outcomes are common in theoretical physics. Solutions often contain features that may never be realized in physical systems. For example, the Kerr solution for rotating black holes includes closed time-like curves in certain regions, but these do not imply that the universe allows time machines. Similarly, the Reissner-Nordstrom solution includes inner horizons whose stability in nature is questionable. The presence of a structure in an exact solution does not automatically guarantee its presence in the cosmos. The distinction between coordinate singularities and physical singularities reinforces this caution. Horizons can appear threatening within one coordinate system, but harmless in another. Singularities may emerge in the equations, but represent only the breakdown of a mathematical description. A physical singularity indicates a breakdown of space-time itself, but even then, the interpretation must be treated carefully. These insights shaped mid-20th century relativity research and laid the groundwork for the modern understanding of gravitational collapse, cosmic censorship, and the possible origins of white hole geometries in quantum gravity. The white hole solution inherits this environment of mathematical rigor and physical skepticism. It stands as a clean, complete region in the extended Schwarzschild manifold, supported by Kruskal-Shekaris coordinates, clarified by Finkelstein's causal interpretation, and displayed elegantly in Penrose diagrams. It occupies a legitimate position within the Einstein field equations, shaped by symmetry, continuity, and the global structure of space-time. Time flows in a particular direction in human experience, and the laws of physics often seem to follow that same orientation. Yet many of these laws, when written mathematically, do not contain an inherent arrow. They appear symmetric, evolving just as easily backward as forward. General relativity, in particular, respects a form of time reversal symmetry at the classical level. Its equations allow spacetimes that unfold through contraction or expansion, infall or emergence, collapse or anti-collapse. The presence of a white hole in the extended Schwarzschild geometry reflects this symmetry directly. If a black hole describes matter flowing inward toward a future singularity, then a time-reversed version describes matter flowing outward from a past singularity. Both arise naturally from the mathematical structure when one considers the full range of solutions allowed by the theory. This symmetry becomes clear when examining the basic formulation of general relativity. Einstein's field equations equate curvature with mass energy, but they do not dictate a preferred orientation of time. Replace time with its negative in the equations, and the curvature remains unchanged. Geodesics can be traced forward or backward, and the geometry maintains its consistency. A collapsing star solution, when time is reversed, becomes an expanding shell of matter. A black hole interior becomes a white hole interior. The reversal alters the interpretation but preserves the structure. In that sense, general relativity behaves like many other classical physical theories. The dynamics allow processes to be run forward or backward without violating the underlying equations. This symmetry, however, is only one piece of a larger framework. In fundamental physics, the most powerful guiding principle of symmetry comes from CPT invariance, the idea that if one reverses charge, parity, and time simultaneously, the laws of nature remain unchanged. Charge reversal exchanges matter with antimatter. Parity reversal reflects spatial coordinates like a mirror. Time reversal inverts the temporal direction. Together, these reversals produce a transformation under which every known physical law maintains its form. The CPT theorem, proven in the mid-20th century, states that any quantum field theory consistent with special relativity must respect this invariance. In the context of spacetime objects such as black holes and white holes, CPT invariance provides intriguing conceptual insights. Consider a particle falling into a black hole. Under time reversal, the particle instead emerges from the horizon. Under parity reversal, its trajectory mirrors. Under charge reversal, its charge flips. A white hole, as an object from which particles emerge along deterministic paths, resembles the time-reversed behavior of a black hole. It does not arise from charge or parity reversal, but from the temporal component of the symmetry. Embedded within the full CPT picture, one can imagine an entire mirrored universe in which white holes appear naturally as the CPT counterparts of black holes. Yet the situation becomes complex when considering thermodynamics. Classical general relativity is symmetric in time, but thermodynamics introduces irreversibility. Entropy grows toward the future. Energy disperses rather than concentrates. Complex systems evolve from ordered states into disordered ones. The increase of entropy defines the arrow of time in macroscopic phenomena. Even though the microscopic laws may allow time reversal, the overwhelming statistical behavior of matter selects a preferred direction. A white hole is an object whose behavior appears drastically misaligned with thermodynamic irreversibility. Its very existence requires a low entropy past boundary, a singularity that releases matter in a highly organized manner. In contrast, black holes represent immensely high entropy configurations. A black hole's entropy is proportional to the area of its horizon, a relationship discovered by Jacob Bekenstein in 1972 and later refined through Hawking's thermal radiation calculations. This area-based entropy makes black holes among the most entropic objects in the universe. A white hole, if treated as the temporal inverse of this structure, would correspond to an object evolving from a highly ordered state into an outward flow of matter and radiation. In thermodynamic terms, this equates to entropy decreasing toward the future. Such behavior rarely appears in nature and would contradict the statistical foundation of the second law of thermodynamics. The second law states that closed systems evolve toward configurations with greater numbers of microstates, greater disorder. A white hole, by forcing matter outward in a coherent, directed pattern, behaves like a system producing order from disorder. It resembles an engine running without fuel, a process that reduces entropy spontaneously. This tension reveals why time-reversed solutions do not automatically correspond to physically realized objects. Many solutions permitted by the equations of relativity are filtered out by the additional constraints of thermodynamics. A collapsing star forms a black hole because collapse increases entropy. A white hole would require a finely tuned, extremely improbable starting configuration. While relativity allows it, thermodynamics makes it statistically inaccessible. The contrast between dynamical symmetry and thermodynamic irreversibility becomes even clearer when considering Maxwell's demon, a thought experiment proposed by James Clerk Maxwell in the 19th century. The demon controls a tiny door between two gas chambers. By selectively allowing fast molecules to pass into one chamber and slow molecules into the other, the demon decreases entropy without performing physical work. The thought experiment challenges the second law by describing a system that produces order through selective information use. Modern interpretations resolve the paradox by including the demon's information processing in the entropy calculation. Once that information cost is considered, the overall entropy increases, preserving the second law. The white hole resembles a gravitational analogue of Maxwell's demon. It appears as a cosmic device that sorts matter outward, releasing it in an organized pattern without absorbing or mixing it. It reduces gravitational entropy locally by evolving from a low entropy state at the singularity into a coherent outward flow. Unlike the demon, a white hole has no mechanism attached to it, no intelligence, no selection principle. It performs its sorting passively through the geometry of space-time. Thermodynamics raises the question, what is the origin of the low entropy state required to create such an object? For a black hole, high entropy arises from gravitational collapse. For a white hole, an extraordinarily ordered initial state is required. Such a state would need to be placed into the universe at the earliest moments or encoded into the initial conditions of the cosmos. The mathematical structure does not forbid such a condition, but statistical mechanics makes it extraordinarily unlikely. Nature prefers states with many microstates, and a white hole interior corresponds to a very small set of initial configurations. This distinction illustrates why time symmetry does not guarantee the physical realization of time-reversed objects. The equations may allow a process to be run backward, but the universe may not contain the necessary boundary conditions to make that reversed process occur. Black holes exist because the universe produces many pathways to form them: stellar collapse, mergers, and primordial density fluctuations. White holes, by contrast, require a configuration that entropy strongly suppresses. They do not emerge from realistic physical processes unless those processes originate in an extremely special environment. Time reversal symmetry in general relativity remains mathematically valid, but the universe appears to select only one orientation. The thermodynamic arrow of time points toward increasing entropy. This arrow influences not only statistical systems but cosmological evolution. The early universe, particularly the conditions surrounding the Big Bang, exhibits remarkable low-entropy structure. Roger Penrose has emphasized this point, describing the early universe as possessing gravitational entropy near its minimum possible value. This unusual initial condition sets the direction of time for cosmic evolution. As matter clumps into galaxies and stars, gravitational entropy increases, reinforcing the directionality. Black holes represent the upper extreme of gravitational entropy. White holes represent the lower extreme. If the universe had begun in a highly entropic configuration, white holes might appear naturally as the time-reversed analogues of black holes. Instead, the early universe carried the seeds that favoured expansion, structure formation, and eventual collapse into black holes. White holes require an origin that embeds their low-entropy singularity into the past boundary of spacetime. In the analytically extended Schwarzschild solution, that singularity appears because the mathematics constructs all possible regions of the spacetime, not because nature supplies the boundary conditions. The question then arises, should the time-reversed solutions of general relativity be considered physically meaningful? For some systems they are. A pendulum behaves the same when filmed forward or backward. A planet orbiting a star traces a reversible trajectory. Even electromagnetic waves treat time reversal gracefully. In quantum mechanics, the Schrödinger equation admits time-reversed solutions. But in any scenario where entropy plays a defining role, the reversed behaviour fails to emerge. The distinction lies in whether the system is dominated by conservative, reversible dynamics or by statistical processes that produce irreversibility. A white hole belongs to the second category. Although the underlying equations are reversible, the statistical nature of matter and energy resists reversal. White holes struggle against the second law because they impose order where disorder should prevail. They are sustained by a special boundary condition rather than by a process the universe readily produces. The deeper one explores these reversals, the more tightly the concepts intertwine. CPT invariance shows that the fundamental laws remain symmetric under charge, parity, and time reversal. General relativity extends this symmetry into its global solutions. Yet thermodynamics asserts that entropy chooses a direction. Black holes become the natural structures in a universe governed by increasing entropy. White holes become the theoretical shadows of these structures, visible in the mathematical formulation but obscured by physical constraints. The existence of such shadows carries significance. They show how broad the landscape of possible spacetimes is, and how the laws of physics carve out the subset that the universe chooses to inhabit. They illustrate the interplay between symmetry and irreversibility, between possibility and statistical likelihood. And they highlight the way general relativity accommodates objects defined entirely by reversed temporal evolution, even as the thermodynamic arrow discourages their realization. In 1935, Albert Einstein and Nathan Rosen published a short but influential paper that introduced a structure now known as the Einstein-Rosen bridge. Their purpose was not to describe wormholes as speculative tunnels through spacetime, nor to propose passages to distant regions of the universe. Instead, they were attempting to remove the central singularity in the Schwarzschild solution. The singularity at r equals 0 appeared unphysical to them, and the bridge emerged from an effort to reinterpret the geometry in a way that eliminated that point from the manifold. Einstein and Rosen replaced the radial coordinate with a new one that reflected a doubling of the external region. In this construction, the Schwarzschild exterior appears twice, connected by a throat located at the horizon. The throat links two mirror image regions, each representing a possible spatial universe. At the midpoint of the bridge, the geometry narrows into a smooth, minimal surface. The authors interpreted this surface as a non-singular connection between the two sides. Although they did not describe the structure as a shortcut or a tunnel, they recognized that the geometry showed two separate exterior regions joined by a continuous space-time manifold. From a modern perspective, the bridge is the earliest example of a wormhole in general relativity. The two external universes correspond to Region 1 and Region 3 in the Kruskal-Sakaras extension. The throat sits at the horizon where the Schwarzschild coordinates break down, but the Kruskal geometry remains regular. In this full extension, the Einstein-Rosen bridge is a geometric feature connecting the black hole interior with the white hole interior. Traversing the bridge would require entering one interior and emerging into the other external universe. In the bridge diagram, the white hole interior is the past-oriented region from which geodesics emerge. The black hole interior is the future-oriented region that absorbs all geodesics. Between these two interiors lies the throat. In static Schwarzschild geometry, this throat narrows to a point so quickly that any attempt to cross it fails. The geometry collapses before traversal becomes possible. The bridge exists only as a momentary configuration in the full space-time. It is a geometric possibility, not a navigable path. To understand why the bridge closes immediately, consider the causal structure surrounding the throat. In Schwarzschild coordinates, the horizon is not a place one can hover near indefinitely. Once inside, radial coordinates become time-like. Future-directed paths move inevitably toward the black hole singularity. In Kruskal coordinates, the throat connects these regions only instantaneously in the global time of the diagram. Any slice representing the geometry at a fixed time shows the throat pinching off. A traveller attempting to cross would confront this narrowing. The wormhole collapses faster than any signal or particle could traverse it. This behaviour demonstrates a fundamental property of the Einstein-Rosen bridge. It is non-traversable. It provides a geometric link between two distant regions, but does not allow communication or travel. Matter falling into the black hole interior cannot reach the white hole interior. Matter emerging from the white hole interior does not originate from the opposite exterior region. The two sides remain causally disconnected, even though the geometry mathematically places them on a common manifold. John Wheeler later explored the implications of such structures in the 1950s and 1960s through his program known as geometrodynamics. Wheeler sought to express all physical interactions in terms of the properties of spacetime itself. In this vision, wormholes, quantum fluctuations, and topological features of the vacuum became ingredients of physics. Wheeler introduced the term wormhole, inspired by the idea of a worm burrowing through an apple, creating a path between two distant points on the surface. In Wheeler's work, space-time is dynamic and fluctuating. The geometry may include tiny wormholes appearing and disappearing on very small scales, forming a turbulent structure sometimes described as space-time foam. At these scales, quantum effects become significant. Distances become uncertain, curvature fluctuates rapidly, and topology may change in fleeting ways. Classical general relativity remains smooth, but quantum fluctuations distort the geometry on the Planck scale. The Einstein-Rosen bridge fits into this framework as one of many possible structures that space-time might briefly adopt in a quantum regime. Wheeler imagined that such bridges could appear spontaneously and vanish almost immediately. Their fleeting existence would not permit macroscopic traversal. Instead, they would contribute to the microscopic fabric of space-time. The bridge from the 1935 paper became an example of how classical solutions might inspire quantum interpretations. In classical physics, the bridge is stable only for an instant. In quantum physics, its uncertainty and fluctuations might give it transient presence. Wheeler's ideas inspired decades of research into wormholes, topology change, and the role of geometry in fundamental physics. Yet the classical Einstein-Rosen bridge remained limited by its non-traversable nature. Even hypothetical scenarios based on time-reversed symmetry do not permit travel from one side to the other. A traveller entering a black hole interior encounters the future singularity. The white hole interior emits matter along time-like geodesics from its past singularity. These two interiors cannot be crossed in sequence. The geometry that looks like a tunnel is only a depiction of the global manifold, not a physical corridor. This raises a natural question. If the geometry suggests the possibility of a path, what prevents classical physics from allowing that passage? The answer lies in stability. Wormholes connecting distant regions are inherently unstable under classical gravitational dynamics. Small perturbations, even the presence of a single particle near the throat, cause the bridge to collapse. The collapse is not gradual, it is immediate and dictated by the curvature of the geometry. The more massive the wormhole, the more certain the collapse. The event horizon surrounding the throat ensures that once a perturbation begins, the collapse propagates in a way that closes the passage before traversal becomes possible. Tidal forces reinforce this barrier. The curvature near the interior regions grows extremely large. Any object approaching the throat experiences tidal stretching and compression that would disrupt its structure long before reaching the midpoint. Classical wormholes impose harsh gradients in space-time curvature. Their geometry is not welcoming to travelers. It indicates the limits of motion permitted by the Einstein equations. These classical limitations shape the interpretation of the Einstein-Rosen bridge, yet quantum physics adds layers of complexity. Quantum gravity introduces new energy conditions and fluctuations that do not follow classical rules. Certain quantum fields can produce negative energy densities locally, allowing geometries that classical relativity forbids. In such regimes, wormholes might become stabilized, at least temporarily. Before discussing these possibilities, one concept requires a brief introduction, because it appears frequently in modern theoretical approaches. ADS CFT. ADS CFT is a correspondence discovered in the late 1990s showing that gravity in a curved spacetime with negative curvature, anti-de Sitter space, is equivalent to a quantum field theory living on its boundary. This duality connects geometric structures to quantum information. In such frameworks, wormholes can appear as geometric reflections of quantum entanglement rather than as physical tunnels. The geometry becomes a map of correlations, not a passageway. With this idea in mind, several approaches to quantum gravity revisit wormholes through the lens of quantum fields and holography. Loop quantum gravity proposes that space is quantized on extremely small scales, possibly preventing singularities from forming. In some models, the interior of a black hole undergoes a bounce and emerges into a region resembling a white hole interior. This bounce does not create a traversable wormhole, but it shows how quantum effects can transform the classical picture. In semi-classical gravity, wormholes appear as contributions to the path integrals that govern quantum evolution. They influence correlations between distant points, suggesting underlying geometric connections. In the holographic view inspired by ADS CFT, wormholes represent entanglement between quantum systems. The Einstein-Rosen bridge connecting two entangled black holes becomes a geometric analogy for the underlying quantum correlation, summarized in the idea ER equals EPR. The Einstein-Rosen bridge originated as an attempt to remove a singularity. It evolved into a central example of how geometry, topology, and quantum theory intersect. The classical structure remains non-traversable, defined by its causal boundaries and instantaneous collapse. Yet it continues to guide research into the deep links between space-time and quantum information, showing how a geometry discovered in 1935 grew into one of the most influential concepts in modern theoretical physics. The idea of a white hole emerges cleanly from the mathematics of general relativity, yet the universe appears silent on their existence. If such an object were to form naturally, the process would need to satisfy conditions that differ profoundly from anything observed in astrophysics. Understanding why requires tracing the origins of cosmic structure, beginning from the earliest moments of the universe. The Big Bang is the only event known to involve extreme densities and energies comparable to those associated with white hole interiors. If white holes require specific initial conditions, the early universe is the one environment where those conditions might have existed. From a geometric viewpoint, a white hole interior corresponds to a past singularity that emits matter along divergent geodesics. The Big Bang also marks a past boundary for all matter and radiation from which geodesics diverge. This similarity invites speculation that white holes could arise from the same initial conditions that shaped cosmic expansion. Yet the parallel is limited. The Big Bang is a global boundary of space-time, not a localized region embedded within it. It produced a universe that expanded uniformly on large scales. A white hole, by contrast, is a localized structure with a well-defined horizon and a specific causal arrangement. To form one, the universe would need to embed a region whose boundary behaves like an anti-trapped surface. That region would require initial data arranged so precisely that all future directed paths through the interior lead outward across a horizon without any incoming matter. These requirements are extraordinarily restrictive. They demand that the interior be perfectly empty of infalling radiation, perfectly symmetric, and perfectly aligned with the curvature needed to generate the time-reversed structure of a black hole. General relativity provides no natural mechanism for assembling such conditions. During the first fractions of a second after the Big Bang, the universe was hot, dense, and turbulent. Quantum fluctuations seeded the distribution of matter. Inflation smoothed large-scale curvature, but did not eliminate small-scale variation. In such an environment, a region would have struggled to maintain the pristine configuration required for a white hole. Any small disturbance, incoming radiation, asymmetrical density, or a gravitational wave passing nearby, would distort the anti-trapped surface and collapse the geometry. Unlike black holes, which form from irreversible gravitational collapse, white holes demand isolation from the very processes that dominate the early universe. Astrophysical processes today do not create such configurations either. Stars undergo gravitational collapse when nuclear fuel is exhausted. Their cores contract until electron degeneracy pressure or neutron degeneracy pressure cannot counteract gravity. If the mass exceeds a critical limit, collapse continues past all known pressure supports. The geometry around the collapsing star approaches that of a black hole. Horizon formation marks the end of any outward-directed causal paths. The collapse process is driven by the concentration of mass energy and the increase of gravitational entropy. An anti-collapse process, the reverse of gravitational collapse, would require a star to reverse its evolution, shedding energy in a precisely tuned pattern that expands outward from an interior singularity. The entropy would decrease in the process, and the matter distribution would need to evolve backward through each stage of stellar evolution. No known physical mechanism supports such behavior. Nuclear processes proceed toward lower energy states. Gravitational binding increases entropy as matter clumps. Electromagnetic radiation emitted by stars carries entropy outward. None of these processes suggest the existence of a pathway toward forming a white hole. Phase space arguments reinforce this conclusion. Phase space is the mathematical space of all possible states of a system. The number of possible high-entropy states dwarfs the number of low-entropy states. Gravitational systems, in particular, have immense phase space volumes corresponding to collapsed objects like black holes. A black hole maximizes entropy for a given mass, following the relation between its horizon area and its entropy. A white hole, by contrast, represents a tiny region of phase space, a set of states so finely tuned that they occupy an extremely narrow slice of all possible configurations. The second law of thermodynamics suggests that systems evolve towards states occupying larger regions of phase space. Black holes sit at the natural endpoint of gravitational evolution. White holes occupy the opposite extreme, and spontaneous evolution toward them is overwhelmingly improbable. Even if the equations allow white holes, the statistical weight of their configurations is negligible compared to the weight of configurations that produce black holes or other high-entropy outcomes. The constraints become sharper when considering the behavior of curvature during cosmic inflation. Inflation expanded a tiny patch of space-time exponentially, smoothing curvature and producing nearly identical conditions across vast distances. During this expansion, density variations were generated through quantum fluctuations, later growing into galaxies and clusters. Yet inflation does not produce localized anti-trapped surfaces. It constructs a global geometry, not a pocket with the specific causal orientation required for a white hole. If inflation resulted in white holes, their signatures would appear in the cosmic microwave background as localized anomalies with characteristic patterns of divergence. No such patterns have been found. Certain speculative models explore conditions that might precede the Big Bang, such as bouncing cosmologies or cyclic universes. In these models, an earlier contracting phase precedes expansion. If quantum gravity causes the contraction to reverse, the bounce could resemble a white hole-like structure. However, these models also face constraints. The bounce is typically global, not localized. The curvature at the bounce does not form horizons or anti-trapped surfaces in the classical sense. The white hole analogy is useful conceptually, but does not imply the existence of actual white hole objects within spacetime. In some theories, quantum effects might stabilize a region long enough to produce temporary behavior resembling a white hole. Yet the stability problem remains. Classic white holes are unstable under any perturbation. Even a single particle entering the region outside a white hole's horizon can collapse the anti-trapped surface. The presence of radiation, gravitational waves, or ambient matter, all ubiquitous in the early universe, would disrupt the delicate geometry. A structure requiring complete absence of infalling matter is incompatible with a universe filled with interacting fields. This instability also explains why classical general relativity disallows white hole formation after the earliest moments of cosmic evolution. Once the universe expands and matter begins to interact, no mechanism exists to carve out a region isolated from all incoming degrees of freedom. Black holes form through processes that amplify density. White holes require the inverse, suppression of all external influence. The equations demand that the region be shielded from any disturbance, yet the universe provides no such environment. The issue becomes even more pronounced when considering gravitational entropy. A white hole possesses lower gravitational entropy than a comparable black hole. The formation of a low-entropy object late in cosmic history goes against the natural trend. This is not merely statistically unlikely, it contradicts the directional behavior of gravity in a universe dominated by structure formation. As matter collapses into stars, galaxies, and black holes, gravitational entropy increases. White hole formation would imply a local reversal of this trend, reducing entropy by imposing strict order on the configuration of matter and curvature. These constraints frame the difficulty of forming white holes naturally. They are geometrically legitimate but astrophysically inaccessible. Their formation requires initial data so finely tuned that astrophysical processes cannot produce them. Collapse generates black holes. Expansion generates cosmic structure. No known mechanism supports the anti-collapse or the precise density configuration required for a white hole's horizon. Even speculative ideas in early universe cosmology must contend with the demands of stability and entropy. Inflationary models produce large-scale smoothness, but do not generate localized white hole regions. Pre-Big Bang models may produce bounces but do not generate classical anti-trapped surfaces. Quantum gravity might alter singularities, but classical exterior geometries still require boundary conditions incompatible with natural formation. The combination of entropy, phase space constraints, instability, and the absence of any astrophysical production pathway shapes the scientific understanding of white hole formation. They arise cleanly in equations, but resist physical realization because the universe does not supply the required boundary conditions. The existence of black holes as astrophysical objects is no longer in doubt, yet their long-term fate remains one of the most scientifically rich questions in modern physics. Classical general relativity predicts that once a black hole forms, it persists indefinitely unless disrupted by external forces. But in 1974, Stephen Hawking introduced a quantum mechanical insight that reshaped this understanding. Black holes emit thermal radiation through processes occurring near the horizon, a phenomenon now known as Hawking radiation. This emission slowly reduces the black hole's mass. Over vast timescales, the black hole can evaporate entirely. The evaporation process proceeds extremely slowly for astrophysical black holes. A stellar mass black hole with a mass comparable to a few suns would take on the order of 10 to the 67th power years to evaporate, far beyond the current age of the universe. Supermassive black holes with millions or billions of solar masses require even more staggering durations, up to 10 to the 100th power years or more. In the foreseeable cosmic future, these objects remain effectively stable. But on theoretical timescales, evaporation becomes inevitable. The black hole shrinks, its temperature rises, and the process accelerates toward the final stages. It is within this quantum gravitational end phase that some researchers see a path toward white hole behavior. As the black hole contracts, the curvature at the center increases. Eventually, the classical description of the singularity becomes inadequate, and quantum effects must dominate. This leads to questions about how quantum gravity modifies the interior. One possibility is that the collapse halts at extremely small scales due to quantum pressure or discrete spacetime effects. In this view, the singularity never forms. Instead, the black hole interior undergoes a transition that reverses the direction of evolution. Loop quantum gravity, LQG, a theoretical framework that quantizes spacetime itself, provides one version of this idea. In LQG, space is composed of finite, discrete building blocks. Curvature cannot diverge continuously. As matter and energy approach Planck scale densities, the discrete structure resists further contraction. The result is a bounce, a reversal of the collapse that sends matter outward. This outward evolution is mathematically similar to the time-reversed behavior of a black hole interior. The expanding region resembles a white hole interior, not in the classical sense, but as a quantum extension of the original black hole. In this scenario, the black hole does not evaporate into nothing but transforms into a white hole that releases the information and matter it once absorbed. The timescales involved can be immense. The bounce might occur only after the black hole has evaporated significantly, leaving behind a small remnant, or the bounce might occur early, within extremely short interior timescales, but appear much later from the perspective of an outside observer due to gravitational time dilation. Carlo Rovelli and Francesca Vidotto have explored this idea extensively. In their models, the evaporation process does not end in a complete disappearance, but instead transitions into a Planck-scale white hole remnant. The remnant is stable because its horizon radius is extremely small, on the order of the Planck length. It continues to exist indefinitely, carrying the information that once fell into the black hole. In this picture, white holes appear as the final stage of black hole evolution. They are not primordial objects, but quantum gravitational remnants, extremely small and extremely long-lived. These remnants are compelling for several reasons. They provide a mechanism for resolving the information paradox, the question of whether information is destroyed inside a black hole. In classical evaporation, Hawking radiation is thermal and seemingly devoid of information about the matter that formed the black hole. But if the evaporation ends with a white hole remnant, the information can re-emerge gradually or be stored indefinitely. The remnant acts as a container for quantum information. Its white hole-like behavior allows for the possibility of eventual leakage in ways consistent with quantum mechanics. Information leak through a white hole phase would be subtle. Tiny amounts of energy could be emitted as low-frequency radiation over extremely long periods. The process would resemble slow decay rather than explosive release. The remnant would not resemble a classical white hole. It would exhibit quantum behavior dominated by its microscopic structure. The emission might contain correlations that encode information in ways compatible with unitarity. Such remnants have been proposed as potential dark matter candidates. Dark matter is known to constitute most of the mass in galaxies, yet it interacts weakly with radiation and ordinary matter. A population of Planck-scale white hole remnants would be massive individually, but tiny in size, interacting primarily through gravity. They would be invisible to electromagnetic observation, yet contribute to gravitational pull. Rovelli and Vidotto have argued that if black holes formed abundantly in the early universe, their remnants could persist today, forming part of the dark matter. The strength of this hypothesis lies in its natural emergence from quantum gravity. If black holes inevitably produce remnants, then a population of such remnants would accumulate over cosmic time. Their stability ensures longevity. Their mass contributes to galactic halos. Their absence of large-scale interactions matches dark matter behavior. However, the hypothesis also faces challenges. The abundance of black holes required to produce the observed dark matter density is unclear. Stellar collapse alone cannot account for it. Primordial black hole formation would need to contribute significantly. The distribution of remnants must also match the smooth distribution of dark matter inferred from gravitational lensing and galactic rotation curves. Another difficulty lies in observational testing. Planck-scale remnants would be extraordinarily small and emit negligible radiation. Detecting them directly is virtually impossible with current technology. Their gravitational effects would be indistinguishable from other forms of cold, dark matter. They might produce rare bursts of radiation if they interact or collide, but such events would be extremely unlikely. The hypothesis remains speculative but scientifically intriguing because it connects quantum gravity, information theory, and cosmology. The possibility of detecting tiny white hole remnants through astrophysical observations has prompted researchers to explore scenarios in which remnants emit brief, energetic signals. These emissions would arise if quantum transitions allow remnants to release stored energy in sudden bursts. Such bursts could resemble fast radio bursts, FRBS, intense millisecond duration signals detected by instruments like CHIME. FRBs have uncertain origins. Some arise from magnetars, but others remain unexplained. A small fraction of FRBs might reflect exotic processes, and theorists have considered whether white hole remnants could produce signatures within detectable frequency ranges. The idea is speculative. The energy scale of a Planck-size object is immense, but the emission mechanism would depend on quantum transitions not yet modelled fully. If remnants emit radiation at radio frequencies, their bursts would be extremely rare. The distribution of FRBS across the sky does not strongly support this model, but it cannot be entirely excluded. CHIME continues to detect new FRBS, including repeating events and highly energetic single bursts, offering a data set against which theoretical models can be tested. Gamma-ray emissions provide another potential signature. The Fermi Gamma-ray Space Telescope monitors the sky for brief high-energy events. If white hole remnants decay suddenly, they might release gamma rays or even heavier particles. Such emissions would appear as short gamma-ray bursts without accompanying signals from supernovae or neutron star mergers. Fermi has detected unexplained gamma-ray flashes, but none have been definitively linked to exotic compact objects. The challenge lies in distinguishing rare exotic events from the background of astrophysical bursts produced by magnetars, black hole accretion, and relativistic outflows. Constraints from Fermi limit the number of explosive high-energy events that could originate from white hole remnants. If remnants were too common or too active, they would produce an excess of detectable gamma rays. The observed distribution shows no such excess. This places upper bounds on the abundance and activity of Planck-scale remnants. CHIME provides similar constraints in the radio band. These constraints do not eliminate the possibility of remnants, but narrow the parameter space in which they might exist. One of the most significant implications of a white hole remnant model is its tie to quantum gravity. Classical general relativity predicts singularities, but many physicists believe that quantum effects must modify or eliminate these infinities. The black hole-white hole transition is one way to avoid singularities, replacing them with smooth quantum geometries. Loop quantum gravity remains one of the few frameworks where this transition has been explored quantitatively. Other approaches, such as string theory, explore holographic dualities and entanglement-based descriptions of black hole interiors, but the explicit formation of white hole remnants is less central in those models. The notion of information leak is also closely tied to this transition. If the black hole interior becomes part of a white hole region, the information that fell in could reappear gradually through quantum emissions. This would restore unitarity, ensuring that quantum evolution preserves information. It provides a potential resolution to the information paradox without requiring exotic non-local processes or drastic modifications to quantum mechanics. The white hole remnant behaves as a long-term reservoir that releases information at a pace consistent with quantum coherence. These ideas remain under active investigation. They connect black hole evaporation, quantum geometry, and cosmological structure in a single framework. Whether the universe contains such remnants remains uncertain, but the theoretical work illustrates how quantum gravity can transform classical endpoints into new phases of evolution. White hole remnants serve as a bridge between the irreversible collapse described by classical gravity and the reversible dynamics inherent in quantum mechanics, suggesting that deep inside the fabric of spacetime, the boundary between collapse and expansion may not be as absolute as it appears. The question of whether the Big Bang could be interpreted as a white hole arises naturally from the structure of general relativity. A white hole, in the mathematical sense, is a region whose interior lies entirely in the past of every event outside its horizon. All future-directed paths move outward. The Big Bang also sits at the past boundary of all cosmic trajectories. Every particle's world line extends back to a moment where densities and temperatures reach extreme values. This resemblance has led several physicists to explore whether the universe itself might be the interior of a white hole. The idea has roots in early cosmology. Georges Lemaitre, a Belgian physicist and priest, proposed in the 1920s and 1930s that the universe began from what he called the primeval atom, a dense, compact state that expanded outward. Although Lemaitre did not use the term white hole, his conceptual picture reflects some of the same geometric features. The universe emerged from a small, highly ordered region and expanded uniformly. This early model predates the discovery of the singularities predicted by general relativity, yet it captures the essential intuition that cosmic origin involves a boundary from which all trajectories diverge. With the development of general relativity, the Big Bang began to be understood not as an explosion in space, but as an expansion of space itself. The singularity in standard cosmological models is a point where classical equations break down. It resembles the past singularity of a white hole. Both represent edges of space-time rather than physical objects within it. Yet this similarity does not guarantee equivalence. White holes in the Schwarzschild geometry are localized regions embedded within a larger space-time. The Big Bang is not localized, it is global. The entire universe emerged from the Big Bang. No external region surrounds it. Later work explored more complex versions of this analogy. One idea, developed within the Einstein carton theory, involves torsion, a feature of space-time geometry that extends general relativity by allowing space-time to possess intrinsic spin. In the Einstein-Cartan framework, spin density in matter produces a repulsive effect at extremely high densities. This repulsion prevents singularities from forming. Instead of collapsing to infinite density, matter reaches a maximum density and then rebounds. Nikodem Popławski has explored this idea extensively. In his torsion-based cosmology, our universe might have formed inside a black hole located in a larger parent universe. In this model, matter collapsing into the parent black hole reaches Planck-scale densities and undergoes a bounce due to torsion. The rebound creates a new expanding region, our universe, connected to the parent black hole interior. The expanding region resembles a white hole-like structure. From the perspective of observers inside the new universe, the Big Bang corresponds to the moment when expansion begins. From the perspective of the parent universe, the process appears as matter falling into a black hole. This model introduces a striking conceptual shift. Black holes might be cosmic seeds. Each black hole could spawn a new universe through a bounce, with the interior evolving into a region with its own spacetime. The white hole analogy arises because the bounce produces outward-directed geodesics, similar to the divergence of paths from a white hole singularity. The expanding universe inherits the causal orientation of a white hole interior. A related idea appears in models involving spinning black holes. If a black hole in a parent universe is rotating, the interior geometry includes regions where centrifugal effects counteract gravitational collapse. Some researchers have suggested that such rotation could create a passage into a new expanding region. This emerging region would mimic a white hole interior, with matter and energy expanding outward. The Big Bang in this context becomes the emergence of space from a deep region within a spinning black hole. These models raise intriguing possibilities for the structure of space-time. They suggest that universes could form inside black holes and that the Big Bang might not be an ultimate beginning, but a transition from a previous phase. However, these models must confront observational constraints. The cosmic microwave background, CMB, provides a map of the universe when it was only 380,000 years old. Its uniformity is one of the strongest pieces of evidence for the standard cosmological model. If the Big Bang originated as a white hole-like burst from a localized region of a parent universe, the CMB might carry signatures of anisotropy, deviations from perfect uniformity. Measurements from the Planck satellite show that the CMB is isotropic to 1 part in 100,000. This degree of smoothness is difficult to reconcile with the localized geometry of a classical white hole interior. A white hole would typically produce anisotropic expansion, with geodesics diverging more strongly along certain directions. The CMB does show some anomalies, but none match the patterns predicted by a white hole-like origin. The uniformity suggests a global initial condition, not a point-like emergence within a larger space. Inflation offers an explanation for this isotropy. The inflationary model proposes that the universe underwent an extremely rapid, exponential expansion in its early moments. This expansion stretched out any initial irregularities, smoothing the curvature and distribution of matter. Inflation produces a near-uniform CMB and generates the small anisotropies that led to large-scale structure formation. It also predicts a nearly flat geometry for the observable universe. These features match observations remarkably well. Any model proposing a white hole origin must account for inflation's success. A white hole interior without inflation cannot naturally produce the observed uniformity. If a white hole is involved, inflation must either occur inside it or replace its role entirely. Some speculative models combine the two. A white hole-like bounce triggers inflation, which then sets the stage for the standard cosmological evolution. In these hybrid models, the white hole provides the initial divergence of geodesics, while inflation ensures isotropy and structure formation. Even with such refinements, significant challenges remain. White hole interiors possess specific causal structures that differ from the standard cosmological model. Classical white holes include horizons from which particles emerge. The Big Bang, by contrast, is not surrounded by a horizon. It is a moment when the scale factor of the universe approaches zero. All particles share the same boundary condition. A white hole interior evolves within a fixed space-time. The Big Bang involves the creation of the space-time itself. These differences complicate attempts to identify the two phenomena. Testing these ideas requires identifying observable predictions. A white hole-like origin would leave subtle traces in the universe, and several types of signatures have been considered. One possibility involves directional imprints. If early expansion carried even a slight directional bias, that preference might still echo in the cosmic microwave background. Detecting it would require exceptionally precise measurements of the lowest multipole patterns in the CMB, the largest, faintest shapes imprinted on the sky. Another possibility concerns non-Gaussian fluctuations. Standard inflation predicts a very specific statistical distribution of temperature variations in the early universe. A white hole geometry could produce a different pattern, one that bends those statistics away from the inflationary norm. Modern CMB surveys are already sensitive enough to search for such deviations. The behavior of primordial gravitational waves is another potential clue. If a bounce preceded the Big Bang, the structure of that bounce could shift the spectrum of gravitational waves produced in the earliest moments. Future missions, such as LightBird, aim to detect these ancient wave patterns in the polarization of the cosmic microwave background. Even a small deviation from the predictions of inflation would be meaningful. There is also the question of mass distribution. If our universe emerged from deep within a black hole in a parent cosmos, the distribution of matter on the largest scales might carry that geometric heritage. Subtle patterns in how galaxies cluster could reveal hints of such an origin. And finally, there are potential topological signatures, patterns that reflect the global shape of space. A white hole-like beginning could, in principle, leave repeating structures across widely separated regions of the sky or correlations that standard cosmology would not naturally produce. These considerations show how the structure of the early universe could, in theory, reveal whether cosmic origin involved a deeper geometry. The search continues through observations, theory, and simulation, exploring the possibility that the universe's beginning may be connected to a more complex structure embedded in spacetime. The information paradox began as a subtle question about black holes and evolved into one of the most significant issues in theoretical physics. In 1974, Stephen Hawking published calculations suggesting that black holes emit radiation due to quantum effects near the event horizon. This radiation is thermal, carrying no imprint of the matter that originally formed the black hole. If the radiation continues until the black hole evaporates entirely, the information contained in the initial matter appears to vanish. Between 1974 and 1976, Hawking developed this argument into a claim that black hole evaporation destroys information, violating the principle of unitarity in quantum mechanics. Unitarity requires that physical evolution preserves information. In quantum theory, the wave function evolves deterministically through unitary transformations. Even when decoherence makes information inaccessible, it still exists in principle. Hawking's calculation challenged this foundation by suggesting an evolution from a pure quantum state into a mixed thermal state, a transition forbidden by standard quantum mechanics. The paradox lies in reconciling the geometry of black holes with the rules governing microscopic physical laws. One of the simplest conceptual responses to this paradox involves white holes. If black holes absorb information, a time-reversed object could emit it. In the extended Schwarzschild solution, the white hole interior acts as a source of geodesics, releasing matter and radiation that appear to emerge spontaneously. If a black hole's final stage transitions into a white hole phase, the information it once contained might reappear. This possibility has been explored in several quantum gravity frameworks, offering a potential bridge between the irreversible nature of classical collapse and the information-preserving structure of quantum mechanics. The appeal of this idea stems from the causal structure of a white hole. In a white hole geometry, all future-directed paths lead outward. Nothing enters the interior, everything emerges. If a black hole could transition into such a region as it shrinks to Planck-scale dimensions, information could be expelled gradually or through bursts of quantum emission. This would restore unitarity, by ensuring that the combined evolution, collapse, evaporation, and final white hole release forms a complete cycle in which no information is destroyed. However, incorporating white holes into the information paradox requires more than a geometric analogy. It demands a physical mechanism that transforms a black hole interior into a white hole interior. Classical general relativity provides no such mechanism. The transition must arise from quantum gravity. Several theoretical models explore this possibility. Loop quantum gravity suggests that the interior of a black hole may undergo a bounce, turning contraction into expansion. In such models, white hole behavior emerges naturally as the time-reversed phase of the black hole interior, allowing the release of trapped information. Other approaches rely on holography, particularly the insights provided by ADS CFT. In the ADS CFT correspondence, a black hole in anti-de Sitter space has a dual description in a conformal field theory living on the boundary. This dual theory evolves unitarily. Every process involving the black hole, including its formation and evaporation, must therefore preserve information. From the boundary perspective, information never disappears. It is encoded in the quantum state of the field theory. This duality strongly suggests that black holes cannot destroy information, even if the classical calculation appears to imply that they do. In this framework, white holes acquire an interesting conceptual interpretation. Time-reversed geometries appear naturally in holographic descriptions. A white hole can be seen as the space-time representation of processes that, in the boundary theory, correspond to time-reversed correlations. The holographic view does not require the physical existence of white holes. Instead, it treats them as part of the full set of geometries consistent with gravitational path integrals. They become one of the possible saddles, geometric configurations, that contribute to the quantum description of black hole evolution. This raises the question of whether white holes play a role in preserving unitarity. If the full quantum gravitational description involves a sum over geometries, including time-reversed ones, white holes could appear virtually as contributors to the amplitude of a black hole's evolution. Their role would not be to exist as physical objects, but to help encode correlations between incoming and outgoing radiation. In such a picture, information escapes not through a literal white hole, but through the structure of quantum space-time. Some theorists propose that white holes, or white hole-like remnants, hold information until late times and then release it. Others argue that the holographic principle ensures that information remains encoded at the horizon and leaks out slowly through correlations in Hawking radiation. Both perspectives aim to maintain unitarity without requiring information to vanish. Yet despite the conceptual appeal, most physicists reject the idea that actual white holes exist as astrophysical objects. Classical white holes are unstable. Any incoming matter, even a single photon, would disrupt the geometry and cause the horizon to collapse. The universe is filled with radiation and particles. Maintaining a perfect white hole exterior is almost impossible. Even if a white hole formed in the early universe, the surrounding environment would collapse it instantly. These instabilities suggest that white holes cannot persist long enough to serve as sources of information in a realistic setting. Another difficulty lies in matching white hole behavior with the detailed predictions of Hawking radiation. Hawking radiation emerges from quantum fields near the horizon. It does not involve matter escaping from the black hole interior. The thermal spectrum arises from the geometry of the horizon, not from deep regions of spacetime. If a white hole were responsible for restoring information, its emission would need to produce radiation carrying detailed correlations that match the information content of the original matter. This emission would differ substantially from the thermal radiation predicted by Hawking. It is unclear how such a transition would occur consistently. Even in quantum gravity frameworks, the connection between white holes and information remains speculative. Loop quantum gravity models propose that black holes bounce into white holes, but these transitions depend on assumptions about the discrete structure of space-time. The details of how information is preserved during the bounce remain under investigation. Holographic models, while powerful, treat white holes as part of the mathematical landscape rather than physical entities. Why then do some theorists keep white holes in the discussion? One reason is the conceptual clarity they offer. They represent the cleanest time reversal of black hole physics. If collapse leads to a phase where all paths point inward, the mirror of that process leads to a phase where all paths point outward. This symmetry appeals to theoretical intuition, particularly when considering the deep relationship between time, causality, and geometry. White holes provide a way to visualize how information trapped in a collapsing region might re-emerge without violating physical laws. Another motivation is the desire to avoid singularities. In classical general relativity, singularities represent points where curvature becomes infinite and the laws of physics lose predictive power. Replacing singularities with bounces that lead to white hole-like behavior removes the need for such breakdowns. This aligns with the belief that quantum gravity should eliminate singularities entirely. Finally, white hole models encourage exploration of alternative approaches to the information paradox. They provide a conceptual framework that challenges assumptions about the irreversibility of collapse and the nature of event horizons. Even if white holes do not exist as physical objects, their presence in the mathematical landscape pushes theorists to consider whether time-symmetric or bounce-based solutions could preserve information without contradicting observed physics. The information paradox remains an open question. White holes occupy a unique position in the discussion, part mathematical artifact, part conceptual tool, and part speculative endpoint of quantum gravitational evolution. Their role reflects the broader struggle to reconcile the unitarity of quantum mechanics with the causal structure of black holes, suggesting that the full resolution of the paradox may require a deeper understanding of space-time at the quantum level. If a white hole existed somewhere in the universe, its appearance would be unlike any known astrophysical phenomenon. A black hole signals its presence through accretion, jets, and gravitational influence. A white hole, by contrast, would announce itself only when it acts, when it releases everything previously trapped in its interior. In classical general relativity, a white hole ejects matter suddenly, as if reversing the long history of gravitational collapse. But the universe provides no confirmed examples of such events, so theorists must ask what an observable white hole should look like. The expected behavior depends on scale. A white hole formed through a quantum bounce of a stellar mass black hole might expel an enormous amount of matter and radiation. That outburst could rival the most violent transient events known: gamma-ray bursts, supernovae, and magneta flares. The release would occur rapidly, driven by the geometry of the interior. A white hole does not gradually radiate energy. It disgorges matter in a single outward surge. The timescale could be short, seconds, milliseconds, or even less. The result would be a singular flash, an event that occurs once and never repeats. One challenge is that the universe already hosts phenomena that resemble powerful outbursts. Gamma-ray bursts, discovered in the late 1960s, are intense flashes of high-energy radiation that last from milliseconds to minutes. They originate from massive stellar collapses or neutron star mergers. Fast radio bursts, detected at radio frequencies, last only a few milliseconds, yet release vast amounts of energy. These events come from magnetars or unknown compact objects. A white hole event might fit within the same observational categories, making it difficult to distinguish from more conventional explosions. To identify a white hole, astronomers must look for signatures that do not match established astrophysical mechanisms. One possibility is the sudden ejection of a large mass of material without a corresponding collapse phase. Gamma-ray bursts from stellar collapse follow a predictable pattern. the progenitor collapses, forms a black hole, and emits energy through jets. Neutron star mergers produce gravitational waves along with electromagnetic emission. A white hole event, by contrast, would lack any precursor. It would emerge from empty space, with no detectable object or system preparing the way. The explosive release would appear untriggered, as though matter materialized abruptly. Electromagnetic telescopes search for such anomalies. Instruments like Swift and Fermi scan the sky for gamma-ray flashes. Numerous bursts have been catalogued, and each is classified based on duration, spectral hardness, and afterglow properties. A white hole burst might appear unusual in its spectrum or energy distribution. It might be shorter or more intense than typical events, or lack the afterglow associated with shock waves in surrounding material. Some gamma-ray bursts show no clear progenitor, but none exhibit the specific combination of features predicted for a white hole. Radio telescopes continue the search at lower frequencies. CHIME, located in Canada, detects fast radio bursts with remarkable efficiency. It records thousands of FRBS, including both repeaters and one-time events. A white hole, in principle, could produce a burst in the radio band if its emission involves low-frequency radiation. Such a burst would need to be extremely short and intense, consistent with CHIME's detection window. It would also need to be a one-time event, reflecting the fact that a white hole should not repeat after ejecting its contents. Several fast radio bursts meet the single event criterion, yet their energy scale and dispersion characteristics fit better with magnetar models. Neutrino observatories provide another avenue. The IceCube detector at the South Pole monitors high-energy neutrinos arriving from cosmic sources. Neutrinos are excellent probes of violent astrophysical events because they escape from dense matter long before photons do. A white hole outburst could produce a burst of high-energy neutrinos. IceCube has detected several neutrino events with unknown origins, including some correlated with blazar flares. None, however, exhibit the specific characteristics expected from a sudden, unexplained mass ejection. The absence of clear detections places constraints on white hole hypotheses. If white holes were common, telescopes should have seen events that cannot be linked to known astrophysical mechanisms. The fact that all observed transients match established categories suggests that white holes, if they exist, must be extremely rare or extremely small. A Planck-scale white hole remnant might emit only faint radiation well below detection thresholds. In such a case, telescopes would never observe the event, and the white hole would remain hidden. Another issue is probability. The conditions required for a white hole to form naturally are highly restrictive. If white holes arise only from quantum bounces inside black holes, the universe might contain a population of tiny remnants. Their outbursts, if they occur at all, might be rare events separated by billions of years. The chance of observing a white hole during the age of modern astronomy would therefore be low. This does not eliminate the possibility, but it reduces the expectations for detection. The idea of a one-time transient explosion remains intriguing. A white hole should produce exactly one outburst and then disappear from observational reach. This aligns with some observed features of short gamma-ray bursts or single FRBs, but those events also have well-supported explanations rooted in neutron star mergers and magnetar activity. To distinguish a white hole, astronomers would need to identify a transient that falls outside these frameworks. Such an event might exhibit no gravitational waves, unlike neutron star mergers, no afterglow consistent with shock interactions, no host galaxy or stellar environment, an energy spectrum inconsistent with known explosive mechanisms. To date, no such event has been identified. Future telescopes may improve the search. The Vera Rubin Observatory's LSST survey will map the sky repeatedly, capturing transient events with extraordinary sensitivity. LSST will detect optical outbursts that last seconds to hours, providing clues about unusual cosmic phenomena. A white hole event might produce a flash in optical wavelengths, expanding the range of detectable signatures. The Nancy Grace Roman Space Telescope and the Euclid mission, both focused on cosmological observations, will also monitor wide areas of sky. Their sensitivity to infrared and visible light could reveal transient signals that escape detection in gamma-ray or radio bands. If a white hole emits across a broad spectrum, Roman and Euclid might catch the faint tail of such an event. Multi-messenger astronomy further increases detection potential. Facilities capable of detecting gravitational waves, neutrinos, gamma rays, and radio bursts together provide a comprehensive view of transient events. A white hole event might lack gravitational waves but produce neutrinos and gamma rays. Or it might emit radio waves but no afterglow. By cross-referencing signals across instruments, astronomers can identify anomalies that do not match known systems. Despite the absence of confirmed detections, the search for white holes continues because they represent a boundary condition in space-time physics. They challenge assumptions about time symmetry, causality, and the life cycle of black holes. Detecting one would provide unprecedented insight into quantum gravity and the behavior of extreme curvature. The difficulty lies not only in the rarity of such objects, but in distinguishing them from the universe's many spectacular and familiar explosions. Some theorists argue that white hole signatures might be subtle rather than dramatic. Instead of explosive ejections, a white hole remnant might emit faint, steady radiation or occasional pulses. These signals could fall below current detection thresholds. If so, future observatories with greater sensitivity may reveal patterns that today blend into the background. The observational pursuit of white holes is therefore a search at the edge of astrophysics, looking for events that violate expectations, appear without precursors, and resist classification. It requires patience, precision, and the willingness to question whether space-time might behave in ways only hinted at by general relativity. The elegance of white holes in general relativity comes from symmetry. If the equations allow a region where everything falls inward, they also allow a region where everything is forced outward. Mathematically, the white hole is simply the time-reversed version of a black hole. Its interior contains a past singularity, and nothing can cross its horizon from the outside. Particles and light emerge, travel outward, and never return. In diagrams, it appears as a clean mirror of black hole geometry. But this symmetry conceals a fundamental problem. White holes are catastrophically unstable. They exist only in idealized scenarios that cannot occur in a real universe filled with matter, radiation, and fluctuations. The moment any disturbance enters the region outside a white hole's horizon, even something as small as a single photon traveling in the wrong direction, the geometry collapses. Instead of ejecting matter outward indefinitely, the white hole transitions into a black hole almost instantly. This instability is not a minor complication. It is an inherent feature of the solution. The key argument behind this conclusion was articulated in 1974 by Douglas Eardley. Working within classical general relativity, Eardley analysed how white hole horizons behave when subjected to small perturbations. His result was straightforward. A white hole cannot remain a white hole in any realistic environment. The reason lies in the causal structure. White holes are defined by the absence of infalling matter. They require a vacuum exterior free of disturbances. But real space-time is never empty. Even the cosmic microwave background fills every region with photons. Gravitational waves pass through space constantly. Small density fluctuations permeate every environment. A white hole's clean geometry cannot tolerate any of these influences. Consider what happens if a tiny amount of matter approaches the horizon from the outside. The white hole solution assumes that nothing crosses inward. The horizon is one way in the outward direction. But matter falling toward the horizon curves the surrounding space-time. As it approaches, the geometry adjusts to accommodate the additional mass energy. This deformation alters the position of the horizon, reshaping it into one consistent with a black hole rather than a white hole. In classical relativity, horizons form around regions where mass accumulates. The moment infalling matter is present, the system naturally evolves into a black hole geometry. Erdely's analysis showed that this process does not require large disturbances. A single photon travelling in the wrong direction is enough. Even vacuum fluctuations in quantum fields can provide the perturbation necessary. This sensitivity arises because white holes sit at a delicate boundary between expanding and collapsing geometries. They require a perfect balance, one that cannot be maintained in a universe filled with energy. As soon as the balance is disturbed, the system slides toward collapse. The white hole horizon turns inward, the expansion halts, and the causal structure transforms. What was once a region from which particles emerge becomes a region into which particles fall. This behavior can be visualized using Penrose diagrams. In the idealized Schwarzschild solution, the diagram includes 4 regions: 2 external universes, a black hole interior, and a white hole interior. These regions connect smoothly in the full extension of the geometry, but this elegant structure relies on perfect symmetry and vacuum conditions. When matter is introduced, the diagram changes. The white hole region shrinks and disappears, replaced by a collapsing structure resembling an ordinary black hole. The transformation is rapid. Unlike stellar collapse, which proceeds over time as mass accumulates, the collapse of a white hole horizon is essentially instantaneous. The horizon is defined by global properties of the spacetime, not by local forces. Once a perturbation enters the region outside the horizon, the geometry adjusts to ensure that geodesics point inward, not outward. The outward flowing paths that define the white hole interior cease to exist. The singularity that once lay in the past of all paths becomes a future-directed endpoint. The entire causal orientation flips. Another way to understand this instability is through entropy. Black holes are stable because they maximize gravitational entropy for a given mass. A black hole is a natural endpoint for gravitational collapse, representing a configuration in which matter has fallen into its most disordered gravitational state. A white hole, however, represents an extremely low entropy configuration. It requires matter to be arranged so precisely that it all emerges outward along specific geodesics. Maintaining this arrangement is statistically impossible in a chaotic universe. The second law of thermodynamics drives systems toward higher entropy, not lower. In this sense, the instability of white holes reflects the same principle that drives stars to collapse and galaxies to form. Gravitational systems prefer disorder. A related argument comes from the behavior of horizons under time reversal. Although the equations of general relativity are time-symmetric, the boundary conditions applied to physical systems break that symmetry. For a black hole, the boundary conditions involve collapse, matter falling inward. Time reversing this event produces a white hole, which requires boundary conditions where matter emerges in a highly coordinated way. But real systems never satisfy such reversed conditions spontaneously. Time reversal symmetry is a feature of the equations, not of the physical processes that unfold in the universe. The asymmetry between black holes and white holes reflects the same directional preference seen in thermodynamics. Systems naturally evolve toward collapse, not expansion. Another way to see this instability is to imagine a white hole in deep space. Even in an apparently empty region, the white hole would be bathed in cosmic microwave radiation. Photons approach from every direction. Each photon carries energy and momentum. As these photons move toward the white hole, they alter the spacetime around it. The process is unavoidable. The white hole cannot shut out incoming radiation. It must interact with the surrounding universe, and that interaction triggers collapse. In principle, one could imagine isolating a white hole perfectly, removing all radiation and matter from its vicinity, but achieving such isolation is impossible, even in theory. The universe does not provide empty regions indefinitely free of incoming influences. Another complication arises from gravitational waves. These ripples in space-time propagate freely across the cosmos. Their passage through the region surrounding a white hole would disturb the geometry just enough to start collapse. The frequency and amplitude of these waves vary, but even tiny distortions are sufficient to destabilize the white hole horizon. The white hole solution demands exact symmetry. Gravitational waves are inherently asymmetrical. Their presence is incompatible with the delicate conditions needed to maintain the white hole. Analytical studies also show that perturbations accumulate. Even if a white hole could exist momentarily, the surrounding environment would continually contribute fluctuations that destabilize it further. The instability grows, not fades. The system does not oscillate or return to equilibrium. It progresses rapidly toward the formation of a trapped surface, the defining feature of a black hole. Once that surface forms, the white hole interior is cut off from the rest of the space-time. Outward-bound geodesics become inward-bound. The region that once emitted matter becomes a region that absorbs it. The implications of this instability extend to all scales. Large white holes, if they formed, would collapse immediately upon interacting with their environment. Tiny white holes would fare no better. The smaller the object, the more sensitive it is to fluctuations. Even quantum-scale perturbations would suffice to trigger collapse. This is why white holes do not appear as astrophysical objects. The universe simply does not support the conditions required to sustain them. Classical general relativity therefore treats white holes as mathematical artifacts, valid solutions to the equations, but not physically realizable structures. They appear in idealized diagrams and serve as conceptual tools for exploring time symmetry and the structure of space-time, but their instability ensures that they cannot persist long enough to observe. They self-destruct before we have any chance to detect their outward explosion. The instability problem is one of the clearest reasons why white holes remain hypothetical. Their existence requires a universe perfectly empty, perfectly symmetric, and perfectly isolated, a universe that bears no resemblance to the one we inhabit. Even if one were to form through exotic mechanisms, it would collapse into a black hole almost immediately, leaving no observable trace of its brief appearance. The environment of the cosmos is too dynamic, too filled with energy, too noisy for a white hole to survive. White holes sit at the intersection of geometry, time symmetry, and the deepest unresolved questions in physics. Classical general relativity treats them as mathematically valid but physically implausible. Yet quantum gravity, which seeks to unify the smooth geometry of space-time with the discrete logic of quantum mechanics, opens new conceptual pathways. Across different theories, white holes appear in varied forms, sometimes as real transitions, sometimes as emergent structures, and sometimes as fleeting, virtual entities. Each framework reshapes the idea in its own language. Loop quantum gravity offers one of the most developed approaches to white hole-like behavior. In this theory, space-time is built from discrete units, woven together by quantum states of geometry. Distances and areas cannot shrink continuously. They reach a minimal value set by the Planck scale. When matter collapses inside a black hole, the curvature increases until the quantized structure exerts a repulsive force. This prevents the formation of a singularity. Instead of a point of infinite density, the interior undergoes a bounce. In such a model, contraction gives way to expansion. The mathematics suggests that the interior of a black hole evolves into a region resembling a white hole interior with geodesics pointing outward. The bounce occurs deep within the black hole, but gravitational time dilation causes the outward phase to appear extremely delayed from the viewpoint of an external observer. The result is a transformation from a black hole to a white hole remnant. This transition resolves the classical singularity problem and offers a possible resolution to the information paradox. The information trapped inside the event horizon is not destroyed, but carried through the bounce, eventually emerging in the outward phase. This loop quantum gravity picture is not without uncertainties. The details depend on how space-time discreteness is implemented, how quantum states evolve, and how horizons behave under extreme curvature. Even so, it remains one of the clearest paths by which a white hole could arise naturally, not as a primordial object, but as the final stage of black hole evolution. Another approach, causal set theory, takes a different perspective. Here, space-time is not a smooth manifold, but a network of discrete events connected by causal relationships. Geometry emerges from the pattern of these connections. In such a structure, the evolution of space-time is inherently probabilistic. Collapse and expansion are not mirror images, but follow rules shaped by the growth of the causal set. White holes do not appear as strict time reversals. Instead, certain models predict asymmetric evolution. Collapse may lead to a region with limited causal past, while expansion might arise from discrete growth processes that have no classical analogue. In causal set theory, a white hole could manifest as a region where future-directed links proliferate rapidly, indicating an outward flow of causal influence. This would not correspond to the Schwarzschild white hole interior, but to a new type of expanding region produced by the discrete rules governing space-time evolution. Such objects would be transient, emerging from quantum fluctuations and disappearing quickly. They would not behave like classical white holes, but would represent bursts of expansion embedded within the causal structure. String theory introduces yet another perspective. Within the landscape of higher dimensional geometries, branes and compactified spaces, time-reversed solutions appear naturally. Anti-D Sitter adds space, central to many string-theoretic constructions, contains black hole and white hole regions in its extended geometry. But these white holes are not stable. Their instability mirrors that of their Schwarzschild counterparts. Small perturbations collapse them into black holes, and the surrounding energy density in ADS space makes such perturbations unavoidable. The importance of white holes in string theory arises primarily through holography. The ADS-CFT correspondence provides a dual description. A gravitational system in ADS space corresponds to a quantum field theory on its boundary. Time-reversed geometries appear as legitimate solutions contributing to gravitational path integrals. White holes in ADS space represent the gravitational counterpart of time-reversed processes in the boundary field theory. They help encode correlations and structure in the quantum system. Yet this does not imply that white holes exist physically. In holographic models, they function as mathematical tools rather than astrophysical objects. String theory also suggests that white hole behavior might arise in more subtle ways. The geometry of the black hole interior, when described holographically, appears entangled with degrees of freedom at the boundary. Some interpretations of the ER equals EPR conjecture propose that wormholes and their time-reversed structures correspond to quantum entanglement. In this view, a white hole is not a physical emitter of matter, but a representation of correlations in the quantum state. It is part of the dual encoding of information rather than a standalone object. Euclidean quantum gravity introduces another intriguing possibility. In this framework, spacetime can transition between configurations through tunneling processes, much like particles tunnel through potential barriers in quantum mechanics. A black hole might tunnel into a white hole configuration through a non-classical path. This transition is not a physical evolution through time, but a change in geometry, described by a quantum amplitude. The tunneling probability is typically extremely small, but non-zero. Such transitions would occur on microscopic scales, producing fleeting white hole-like structures that appear briefly in the quantum foam. These structures would vanish almost immediately, leaving no lasting influence. Semi-classical gravity occupies an intermediate position between classical general relativity and full quantum gravity. It treats space-time classically while incorporating quantum fields that influence curvature. In this framework, white holes might exist at microscopic scales. Vacuum fluctuations could generate temporary regions where geodesics diverge instead of converge. These objects would not resemble classical white holes. They would be tiny, short-lived distortions. They would behave more like quantum fluctuations of curvature than macroscopic sources of radiation. Even so, they demonstrate how white hole-like phenomena can arise from the interplay of classical and quantum physics. The idea of virtual white holes emerges naturally from these considerations. If space-time at the Planck scale is dynamic and fluctuating, with geometry constantly shifting, short-lived white hole regions could appear spontaneously. These would be analogous to virtual particles in quantum field theory, emerging and disappearing too quickly to observe directly. Virtual white holes would not eject matter in dramatic bursts. Instead, they would contribute subtle corrections to the structure of space-time. They might influence quantum correlations, or modify the behavior of fields at extremely short distances. This space-time foam picture traces back to John Wheeler's vision of a turbulent microscopic geometry. In Wheeler's geometrodynamics, space-time is not smooth but riddled with tiny wormholes, bubbles, and fluctuations. White holes, in this context, are part of the same spectrum of possibilities as virtual wormholes and transient topological changes. None of these structures are stable or macroscopic. They emerge as consequences of quantum uncertainty applied to geometry. Across all these theories, a pattern emerges. Classical white holes, the large, exploding counterparts to black holes, do not fit comfortably into any physically realistic model of the universe. Their instability and the difficulty of forming them remain major obstacles, but quantum gravity allows for modified, scaled down, or reinterpreted versions of white hole behavior. In some theories, they appear as remnants of black hole evaporation. In others, they manifest as features of the space-time foam. In holographic models, they correspond to time-reversed correlations rather than material objects. These perspectives do not revive the classical white hole as a candidate astrophysical object. Instead, they show how deeply the concept is woven into the mathematical structure of quantum gravity. Each theory reshapes the idea, using it to explore transitions, correlations, and the limits of space-time. The white hole becomes not a physical explosion in the cosmos, but a symbol of the deeper symmetries that underlie the laws of nature. The idea of a white hole challenges something fundamental in our intuition, the direction in which time seems to flow. Every experience we have, every memory, every expectation is built around an arrow pointing from past to future. Eggs break, but never unbreak. Smoke disperses, but never gathers itself back into the flame. Stars collapse, but nothing in the night sky appears to uncollapse. The universe presents a world sculpted by irreversibility. White holes are built from the opposite. They offer a picture of a cosmos where processes unfold backward, where matter that once seemed lost reappears, where the geometry itself favors expansion rather than collapse. Even though these objects are unstable in practice, the mathematical possibility forces us to confront a deeper question. Why does the universe choose one direction of time when the underlying laws allow both? The physics of black holes sharpens this contrast. A black hole contains a future singularity, a place where geodesics end, where world lines terminate. It marks an ultimate destination for matter, a gravitational endpoint where the flow of time seems to converge. A white hole contains the opposite feature, a past singularity. Everything in its interior begins from that boundary. Time emerges outward. For observers inside the geometry, the singularity is not a place they approach, but a place they come from. This distinction reflects two versions of spacetime's structure. A future singularity represents collapse. A past singularity represents emergence. Each is compatible with the Einstein equations. The difference lies not in the mathematics, but in the boundary conditions, the choices nature makes. The universe appears to favour futures over pasts. It contains stars that collapse, galaxies that merge, and structures that fall inward under gravity. It does not contain large-scale objects that behave like white holes, ejecting matter in a sudden reversal of collapse. The absence of these time-reversed phenomena suggests that the arrow of time is not just thermodynamic, but cosmological. It is rooted in the conditions at the beginning of the universe. The Big Bang set the stage for everything that followed. Its low entropy and uniformity created a direction in which entropy could increase. That increase manifests in the formation of galaxies, the burning of stars, and the irreversible evolution of matter. A white hole, requiring exquisitely fine-tuned conditions and extremely low gravitational entropy, lies on the wrong side of that arrow. It embodies a direction the universe does not take. This raises philosophical questions about determinism. The fundamental laws, those that govern fields, geodesics, and quantum amplitudes, are time-reversible. They allow evolution to run forward or backward. Yet the universe chooses one orientation. If we reversed momenta, reversed radiation flow, reversed every microscopic motion, the equations would still hold. But those reversed states are not realized in nature. They require boundary conditions that are never met. White holes illustrate this tension. They are not forbidden by physical law. They are permitted by the mathematics. Yet the universe, in its large-scale behavior, rejects them. Something in the way the cosmos began, something in its initial configuration, set a direction that shapes everything we call physical. This has implications for questions about free will and determinism. If the laws permit both directions, but the history of the universe unfolds in only one, does that history emerge from necessity or contingency? Is the arrow of time something fundamental, or is it the result of an immense statistical preference written into the universe's starting point? White holes become symbols for the roads not taken, the solutions the cosmos could have explored but did not. They also expose a gap between mathematical possibility and physical reality. In physics, equations often describe a landscape broader than the world itself. Many solutions exist only as curiosities, geometric fantasies that obey the rules but never appear in the sky. Tachyons, negative mass particles, traversable wormholes, and classical white holes all occupy this mathematical territory. They demonstrate consistency, not existence. In this sense, white holes remind us that mathematical beauty does not guarantee physical truth. The symmetries of the Einstein equations are compelling, yet nature applies those symmetries selectively. The universe permits collapse, but not anti-collapse. It allows black holes, but not their time-reversed counterparts. Understanding why requires more than mathematics. It requires insight into the conditions of the real cosmos. Still, contemplating white holes evokes a certain emotional response. There is something profoundly unsettling and strangely beautiful about imagining a place where time flows outward, where stars might emerge fully formed, cast into existence by the geometry of spacetime. A white hole is a cosmic fountain, a source rather than a sink. It embodies creation rather than destruction. If such an object existed, watching it would be witnessing something impossible by ordinary standards. A star might appear from empty space, moving outward with no precursor. Dust clouds, radiation, or fragments of ancient matter might scatter across space in a burst that defied every expectation of astrophysics. The event would feel like the universe revealing a hidden degree of freedom, a reminder that we see only one version of time's story. The emotional resonance lies partly in contrast. We are used to thinking of gravity as a force that pulls in, that collapses, that consumes. A white hole reverses that narrative. It pushes outward, rejects infall, and rewrites the intuition that gravity only takes. It gives instead. In doing so, it becomes a metaphor for renewal, a cosmic reversal of fate. Even though white holes are not part of our universe, imagining them encourages reflection on the nature of endings, beginnings, and the impossibility of truly reversing what has been lost. Causality, too, becomes complicated in the presence of white holes. A black hole ensures that events cannot influence the outside world after a certain threshold. A white hole ensures that the outside world cannot influence events within. They represent two extremes of causal separation. One hides its future, the other hides its past. Both challenge everyday notions of cause and effect. If the universe contained both structures, spacetime would host regions where the order of events could not be fully known. Observers would encounter boundaries beyond which no information about origins could be obtained. The cosmos would contain zones of ignorance, not imposed by observational limits, but by the fabric of reality itself. In a sense, the Big Bang resembles such a boundary. It is a past horizon, a point beyond which physical theories cannot describe what came before. White holes offer another window into this idea, not as actual objects, but as a conceptual link between what can be known and what cannot. In the end, white holes illuminate a deeper asymmetry. We can fall into a black hole. Nothing can fall out of a white hole. The universe reveals only one of these behaviors. Gravity gathers, compresses, and accelerates collapse. It does not spontaneously reverse itself. The asymmetry is built into the evolution of structure, into entropy, into the flow of radiation across cosmic time. Even if the laws permit symmetry, the cosmos expresses preference. And yet, the thought remains. Somewhere in the mathematical landscape, a white hole sits as a reminder that time could have flowed differently, that the universe might have been a place where matter erupts instead of collapses, where the arrow of time points both ways, where causality becomes a more fluid concept. It is a vision of a cosmos that chose the opposite path, one in which emergence rather than collapse defines the extremes of gravity. Imagining this alternative is not mere speculation. It deepens our understanding of why the universe behaves as it does. It highlights the fragility of time's arrow and the role of initial conditions in shaping reality, and it offers a cinematic reflection. The universe allows us to fall inward toward gravity's depths, but it does not allow the reverse. There is an imbalance between entrances and exits, between what can collapse and what can emerge, between what slips into darkness and what might one day fall out. White holes challenge our sense of time's arrow. They are the mathematical mirrors of black holes, places where everything emerges instead of collapsing inward. Their existence would blur the boundary between past and future, creation and destruction, yet the universe seems to choose only one direction. This asymmetry reveals how initial conditions shape reality far more than equations alone. Imagining a world where stars erupt from space-time instead of falling into it forces us to confront the limits of causality, determinism, and physical possibility. It is a reminder that what can fall in may never fall out, and that this imbalance defines our cosmos.